Just wait for that to go live. So let me just see about getting the link and putting it into the chat window. So that's it, live, get shareable link, and where are we? We'll put it into Capstone Materials. So that should be going there now. Okay. Sorry about that. Okay. We're in, well, after the break last weekend. I hope you had a good President's Day break. We're now in, it's the third week, or third lecture, fourth week of semester. And we've got most of the basics out of the way. I do want to spend a bit of time today on an introduction to complex numbers. We're not going to need to use complex numbers until we get down to about here. So we'll see how that goes. But I've found it's better if I introduce them earlier on and then use them later on, so that people have a chance to maybe remember what they're all about, and so that's the reasoning behind it anyway. So that's our topic list and the progress to date. And I do want to finish off some of the background on linear algebra. Matt, would you mind muting? And that's just to go through a simple example in the from the tutorial. And then I want to talk about complex numbers, and I want to talk about mesh analysis. And I haven't released the next lab yet. I'm aiming to do that later today, probably after our class session. We should be okay. In fact, I'm aiming to try and set up all of the labs between now and the end of semester, so that you know what's ahead of you. That's the current assessment calendar. The other thing I obviously need to set up is some homework assignments. So watch out for homework assignments later today as well. I usually don't like giving things only a short amount of time, so I'll probably won't make them due until the 6th, and the same with the next lab. I won't make anything due for next week, but it means you'll have a couple of things due on the 6th. So that's what I wanted to talk about today. Any questions about the lab? And I've had a few questions via email, so I thought I should go through lab 2, because it's not very clear what is asking, and that's on purpose, right? I would rather you set up your own circuit one way or the other and answer the questions in there, but I'll show you some appropriate ways to do the lab, and then it's up to you which way you choose. And like I said, I want to go through the last two tutorial questions on the sheet, and then I want to think about complex numbers, and I want to introduce the topic of mesh analysis. One of the excuse me, the main complicated pieces that are in this course are 3, maybe 4 algorithms, right? Julio, can you mute, please? And the first algorithm that we're going to come across is mesh analysis. And an algorithm is just a sequence of steps, right? It's a way of codifying how to approach analysis of circuits. And there's more than one way to do it, so there's more than one algorithm. The 2 main ones are mesh analysis and nodal analysis. And then there's another one that helps us simplify circuits so that we can more easily apply mesh analysis and nodal analysis. And that algorithm, that simplification algorithm, is a thing called superposition. But we'll get there eventually. The one I want to talk about today is mesh analysis. Okay, let's go have a look at the lab. Okay, so the lab that's due today is this one, and there's 2 attachments. There's the lab sheet. Let's have a look at what that says. Let's make it a bit bigger so we can read it. Right? The objectives: for a student to verify Ohm's law by calculating and then measuring voltage, current and resistance. For a student to verify Ohm's law by holding one value constant, e.g. the voltage, and increasing a second value, e.g. the resistance, and calculating measuring the effect on the third, e.g. the current. You could do it other ways around, but it's saying keep the voltage constant, change the resistance, and see that what the effect of changing the resistance is on the current. And then I want you to use the passive sign convention to clearly label polarity, current direction, and power dissipation in whatever elements there are. Okay, so we know Ohm's law, V equals IR. The voltage is equal to the current times the resistance. The passive sign convention is, and I haven't, let me do this. I'm going to import that into OneNote, and that way I can draw on it. Okay, now I can draw. Okay, so for passive elements, resistors, which is the main ones we're looking at now, we'll eventually get to capacitors and inductors. The positive direction of current enters the positive side of the element with respect to the voltage. So you've seen this before, right? We have the circuit element, whether it's a resistor, a capacitor, or an inductor, doesn't matter. We label the voltage, so it's the voltage across the element, and then the passive sign convention says that the current flows into the positive side of the terminal, the positive side of the element. The other thing that I don't know whether I've talked about it before is this lab introduces the idea of conductance. And conductance is just 1 on the resistance, right? So if a resistor is measured in ohms, the conductance, capital G is usually what it's used. It uses, so this is ohms. The conductance is measured in Siemens. Right? And as you might expect, if V equals IR, then V is also equal to I on G, right? Because G is 1 on R. Okay, so what you must do, you must demonstrate the 3 objectives. So what you must do, calculate the voltage, current, resistance and power dissipated using Ohm's law, measure the voltage, current and resistance in LT spice and compare these with your calculated values, calculate the power dissipated, do this with at least 3 different resistor values, draw circuit diagrams of how you measured everything, showing that you... Okay, so we need to fire up LT spice. So let's do that. Yeah, where's it gone? There it is. And it's over there. And let's move that up here. And make it big. And then we want to do some drafting. And maybe we want a component. And we want a resistor. Right? And so there's a resistor, and then we want to F2, we want a voltage source. Okay, so one way, and then what was the wire is F3. Let me just put my keyboard tray out, and then I can do that. Right. And then I need to is it net name? Yeah, I'll put a ground on. Right, and then back to F3 so I can connect it all up. Okay, so that is one possible circuit that you could draw for this assignment, right? And we need to set the voltage. Let's make it 12 volts. We need to set the resistor. Let's make it 1 kilo ohm. I think we also need to add a spice directive, right? Dot tran 1 maybe. And oops, let's just drop that there, and then we can run it. And let's just make that a bit small, make it a little bit bigger so we can actually see it. Maybe make that a little wider. And then we need to measure that voltage and measure that current. Now the other thing we can do is we can add a calculated value, right? And one way to add a calculated value is to add the voltage times the current. Okay, so now you can see well, it doesn't actually plot the power now. Remember, P equals VI, but you can see that the power, for some reason, it's not plotting a red line, but it's, I suspect it's under there. We could probably get yeah, so it looks like the power is 144 milliwatts. Right, so you don't actually have to calculate the power yourself. You can get LT Spice to do it. And then what? So the aim is that you should have calculated what you think I is here and what P is, given voltage of 12 volts and the resistance of 1,000, and then you choose another value, right? Maybe this time it's 2 kilo ohms. And then you do the same thing again, measure the current, measure the power, calculate the current, calculate the power, and make sure that they match. And if they don't match, try and explain why they don't match. They should match, but and that is one way to do this lab, right? There are other ways. You could, let's... Yep, go ahead.
Real quick, do we have to use the transient command, or can we use, like, the transient command? It looks like it shows you that graph and has more data on it. I just did the op point command.
Operating point, yeah, operating point command is fine as well. Yep.
So I could just take a screenshot of the operating point, like, data and throw it in my lab results?
Yep, that would be good. It might be, so I haven't finished talking about what to do with the lab results, right? So let's do that before we right. So what I'd like you to do with the lab results is to take a screenshot of each of your circuits, right? And then go to the lab template, which is also attached, right? And if it opens up for me eventually. Now, one thing I probably should have done with this group, it's thinking about it, is talked a little bit more about what should go into a lab report. And I'll talk a bit more now that I've, hopefully it's opening up that spreadsheet for me. It's thinking about it. There we go, it's on the other screen. Let me grab and let me make it much bigger. There we go, that'll do. Okay, so this is the spreadsheet, all right? And normally when you're writing up a lab report, you want to know when it was done. I want to know who it was written by. So put your date, put the date that you did it in there, put your name in there. Because we're doing this all online, you probably don't have a lab partner. I'm okay with you working with a lab partner, provided you put their name in here. Okay? I'm okay with you pairing up. I'd rather you didn't go with 3s or 4s. So if whatever works for you. This is a generic lab report, so you have to put the title in there, so we can go back to our wherever it got to. We can go back here and we can say, we can copy that across. Right, Ohm's law and the passive sign convention, and we could even go back and grab the objectives, right? So right? So they're the objectives. Now, I would prefer to be able to read them all. I would also prefer that they're formatted a bit better than that, right? So because of the way the line breaks are done, I'm going to have to, so don't just cut and paste, make sure it's in a readable, I'm going to have to make it bigger even. There we go. Now it's all readable. Okay. And then there's the data, right? And for this particular one, right, we've got to do two sets. We've got to do VIR calculated and VIR measured. So let's do that. And we're going to do that for 3 different values. So there's a few ways we could do that. I'm just going to do it this way, right? So I'm going to do it by resistance and the voltage and the current, right? And these are the, I'm going to do a merge and center. These are the calculated values, right? And then I want to do resistance, voltage and current. I wish I could type, but it'd be wonderful. And again, I'm going to merge and center those. And these are the measured values, right? And then say I did 1 kilo ohm, 2 kilo ohms, and 3 kilo ohms. And what was it, 12 volts I had there? Oh, and I forgot, I need to actually let me I need to also put the power in there, so I forgot about that. Let me just put the power in there and merge and center again and put the power in there and merge and center there, right? And then the nice thing about the putting the data into a spreadsheet is now I can just use the spreadsheet to do the calculations, right? I don't have to type it into my calculator and then put the numbers in. You could do it that way if that's what you want to do, but I think you should think about doing it this way, right? So V I equals V on R, so that's going to be that one on that one. And that's a problem again because that's just a number, right? So I don't know what 0.012 is, so let's do put the units in the title, and right, so make sure you've got your units there. And in this case, I'm just going to keep it in amps, and my power is in watts. And I'm going to, I don't want to change the width of the columns. So I'm just going to use wrap text so that I can see the text of everything without changing the width. You can change the width if that's your preferred way of doing things. Do it that way. I'm just doing it to suit myself. Provided all the information is there, provided it's readable, I really don't care what your preferred format is, right? And then the nice thing about this, once I did that, I can just drag that down and it should tell me the rest. And then I need to do the power, so that's just going to be the current times the voltage, right? And that's 144 milliwatts. but 0.14 watts. Okay, and then I just effectively the measured ones, it's a bit silly really, but you know, these are pretty much going to be the same because I set the resistance, I set the resistance and I set the voltage in LT Spice, but the ones that are going to be actually measured are those ones there, right? They're the ones that I have to read off LT Spice, and I'm pretty sure we got 0.144 there, and I've forgotten what the current was. And that's pretty much all you've got to do. There is also a couple of other things, the conclusions. Did you show the objectives? Did you achieve the objectives? You've got to tell me that you did, and just to justify it, right? And then we're not using physical equipment, but I do want you to indicate that you used LT Spice, right? And as there's no serial number really, so that doesn't matter. Another thing that was asked for, let me go back, right? Use the passive sign convention to clearly label, right? And the nice thing about Excel spreadsheets is you can insert pictures, right? So what I suggest you do, I took a screenshot of my the first circuit I did anyway, so I'll just show that as an example. Wherever my screenshots directory got to, there it is. Right, and there's my screenshot. Oops, there it is. And I'm just going to move it up here, and I'm going to make it a little smaller, right? So you can put this in the results section. It doesn't have to be that big, right? And the nice thing about most of the Microsoft tools these days, including Excel and PowerPoint, is that I can draw on it, right? So I do that, right, and then I can say, okay, I've got my plus and my minus, they're already there, and because I can write that, and that's going into the positive side of my passive device, and then this is VR1. Okay, and that's effectively what I'm asking you to do. Does anybody have any questions about any of that?
I have a question. So we're gonna have 3 screenshots, one for like 1,000, one for 2,000, and one for 3,000.
Yeah. I think that's easy enough to do, isn't it? Yeah. Just to change the values. Okay. So I think one of the earlier labs, I was okay with you attaching screenshots, but please, from now on, only ever upload a single file. You should be able to put everything into the Excel spreadsheet, including diagrams. You can edit the diagrams, you can annotate the diagram. If you want to do it in some other software and export the image from that other software, if you think that's neater, by all means. But I think my aim is to make your life as easy as possible while still meeting what I'm after, and I think you should learn how to use Excel, because it does a lot.
Real quick,
Yep, go for it.
how did you find power with LT Spice? Because I'm only able to find current.
I typed it in directly, right? So what I did is I said add trace, and then it allows me to type in a it shows me what values there are there, right? There's the voltage at node 1. I don't know if you can read that on the video.
Mm-hmm.
There's the current through R1, and there's the current through V1, and I can just type in, okay, the voltage at node 1 is effectively VR1, so I'm just going to say V voltage at node 1 times the current through R1 is the power that I'm after, and that'll plot me the power right over here. That's you can see that's voltage times current, and it's our 144 milliwatts.
And do you want a screenshot of that graph, or no? You just type it in.
If you want to, but it really I'm only interested in comparing your calculated values with your measured values in LT Spice. So you can just type it in.
All right, thank you.
Okay.
Professor, what was that notation? Can you? It was just it's kind of hard to see on the screen. But
yeah. So let me just what I'll do is let me just take a screenshot of that, and I'll put that into the capstone materials channel. Okay, so that should, and it's the green one, it's basically just V of N001 times I of R1. And just right click, and I'll put that into the chat channel as well. Okay, and that's pretty much all I'm asking you to do for the for lab 2. Any other questions before we move on? Okay, so remember the reason why this format is the way it is because we want to be able to present the information to somebody so that they can reproduce it, right? It's an experiment, and we want to be able to show what we did so that if somebody else wants to do the same thing, and okay, you know, everybody's doing the same thing, so it's not a groundbreaking experiment, but the aim is that when you start doing stuff in real life, you're probably doing stuff somebody hasn't done before, not with that particular piece of equipment, or maybe not necessarily in that company, or whatever it is. So you want to be able to document what you did, so that you can do it again if you want to, if that's needed, or somebody else can do it if you're doing something different, right? So it's a worthwhile exercise, I think. And let me just I won't put the Excel spreadsheet, but I will put the screenshot into the chat channel. If it comes up, there it is. Right, so you can see what I'm talking about there. Okay. Right, and the main aim was for including the diagrams was so that you can draw those circuit diagrams and label the passive sign convention. And don't forget to submit it into Blackboard. Right. Okay, let's move on. So I think I've answered all the lab questions. So the next one is I wanted to look at the last two questions in the tutorial, but I'll do that directly. I won't split us up. So let's have a look at tutorial 1 again. Okay, I think, did we do that one? I can't remember. Let's go back to the linear algebra notes. No, we'd had the we had those ones. So let's have a look at doing this one. Right, so remember what elimination versus substitution is. Elimination is adding or subtracting the two, in this case, the two different equations that we get so that one of the variables is eliminated, and that gives us a very simple equation to solve in one variable, and then we just back substitute to find the value of the second variable. Substitution is more a bit of algebra, getting one variable on one side and the other variable and any constants and multipliers on the other side, and they just use that substitution. Okay, so let's try elimination first, and I'm going to rewrite this matrix equation as a two simple equations, right? So 20x plus 30y, that should be a 0, 30y equals 100, and then 30x plus 50y equals 200, right? And we'll call that one equation 1 and that one equation 2. So what could we do? We could do, let's do 1.5 times 1 minus 2, right? So 1.5 times 1 is 30x plus 45y equals 150, and then our 30x plus 50y equals 200, and we subtract them, right? So those two cancel, we get 0x, and it's going to be minus 5y equals minus 50. Right, and then we can look at that and just say that that means that y equals 10. And then we can go back and substitute that into, say, equation 1. And then we get that 20x plus 300 equals 100. Right, so 20x equals minus 200, subtracting 300 from both sides. So x equals minus 10. Okay, I'm just gonna, I meant to grab my daughter's calculator. Let me just see if I can get her to bring it to me. Okay, and so that's doing that one by elimination, and then substitution. Let's do the substitution version. We've got, well, let's take 1. Thank you. And what have we got? TI-84. That'll do. So we've got substitution, that we're going to take equation 1 and we're going to rewrite it as 20x equals 100 minus 30y, or x equals 5 minus 1.5 y, dividing both sides by 20. Alright, and then substitute, and let's call that equation 3. And we substitute 3 into 2. Right, and then 2 is 30 times 5 minus 1.5y plus 50y equals 200. And what's that? 150 minus 45y plus 50y equals 200. And that's going to be 150 minus 5y, sorry, plus 5y equals 200, or 5y equals 50, or y equals 10, which tallies with what we got before. And then substitute that into 3. Right, back up here, and we get x equals 5 minus 1.5 times 10, right, which is 15. So x equals minus 10. And that all works. We got the same answer, which is good. Now, I'm not quite sure whether I can do this, but let's give it a go. Okay, it's a bigger meat. It's a little large, isn't it? And I'm gonna try, and it's back to front. Let me see if I can I swap the video? Flip horizontal. Maybe that'll be better. It's still a little out of focus, isn't it? Yeah, we'll see. Right, but you can sort of see it, right? So what I'm going to do, let's just see if I can put that there, right? And then what I'm going to do, and I've got to remember where it is, right? So I can do, where are we? I can do, press the second button, the blue one there, and then down above the inverse x, there's a matrix, right? I've got to turn it on. How do we turn it on? I thought I turned it on. There it is. Let's try that again. That's looking a bit better. Right, so second matrix, and I get three. You can't really read that, can you? You get three options. There's names, edit, math and edit, and the names are A through I, probably more. So what I'm going to do is I'm going to scroll over to edit, and I'm going to edit A, and my A matrix is at the moment is a 3 by 2 matrix, but our A matrix is 2 by 2, so I'm going to change the size to 2 by 2, and then I'm going to see, I can, where is it? I can move around in the matrix, right? And I'm going to enter 20. Oops, no, that's not what I wanted. I'm going to enter 20, and then it goes to the next one across, so I'm going to enter 30, and then down 30 again, and 50. Okay, and you can't really probably see it, but that's having entered, yeah, that's not the best, is it? Oh well, but that's entered that A matrix, right? Let me just write it as, I'm entering this one as A, and I'm going to enter this one as B, right? So that's A, and I can now get out of that. So just second matrix, back out of it, and then I'm going to go over to edit again, but now I'm going to go and edit B, and in my case B is still a 3 by 2 matrix, so I'm going to have to change it to a 2 by 1 matrix, right? No, not a 21 matrix, I want a 2. So 2 by 1, right? And then I enter 100 and 200. Okay, and again, you probably can't really read that, but I've got a 2 by 1 matrix there, and I'm entering it that way. Okay, so then I just second matrix out of that again. And what I can do, and I'm just going to actually second quit, get back to the standard calculator, right? Then what I'm going to do is I'm going to select a second matrix and then just hit enter to select matrix A, and then I'm going to hit x to the minus 1, right? So I just hit that button there where it says x to the minus 1, and you probably can't see it, but it's now got, can I get the angle right? Sort of. It's got the A, and it's got brackets around the A, and it's got a superscript minus 1 on it, right? And then I just multiply that by second matrix and select B, right? So then it's what it's looking like now in the, let me draw it up. So what it looks like on the calculator screen now is that. In fact, the matrix B has square brackets around it as well, right? And now if I just hit enter, I don't know whether you can see over this side here, just there. Funnily enough, it says x is minus 10, and I get the answer. I get minus 10 and 10 in the result. So that's one way to do the solve this equation using a calculator. There is another way, and it's a little different. And it uses, so the other thing, if I go second matrix, the middle, excuse me, the middle row on the matrix operation, you can't quite read it there, but it says math, right? And there's a particular, and you've got to scroll down to the B option, which is off the screen, off the bottom of the screen. And let me just see if I can take a picture of that and send it to the Discord chat. Sorry. La la la. Right, so if you have a look at the once that appears in the capstone materials piece, you should see, there we go. Let me do this. I'm going to see if I can download that. Save image. Yeah. Save it to downloads, and I'm just going to see if I can't insert it over here. And downloads image 1. There we go. There we go. Right, so that's the math option. Oops, like you can't see that, can you? Let me go back to mini-me. There we go. Right, so that's the math option, and I've scrolled down a bit because the ref and ref options were off the bottom of the screen, but it's option B we want, ref. Does anybody know what ref stands for?
Row reduced echelon form.
Wow, somebody knew. Yes. Very good. Thank you. Yeah, so it's a particular form of a matrix called row reduced. Well, I don't know if there's row reduced echelon form or a reduced row echelon form, but yes, it's those words. I just don't know which order the.
Yeah, I think it's row reduced.
Yeah.
I think that's what it is. Yeah.
Yeah. Okay. Cool.
I always thought it was reduced row. So there we have it.
I'm not that picky. I'm not a mathematician, so I just so long as you get the words, and I'm not that picky about the order. So what that function lets you do is doing this was a little picky, right? We had to create two matrices, and then we had to do this this multiplication of the inverse times the other one, right? What row reduced? Whatever. Now you confuse me. Row reduced echelon form does is it lets you just create a single matrix, and the matrix, and let me see if I can find a place for it. Let's just do it over here, right? So the matrix that you can create is 20, 30, and then you augment that matrix with the other stuff you know, right? So you put the 100 there, and then you get the 30 and the 50, and you have the augmented piece there as well, right? So now instead of having a 2 by 2 and a 2 by 1 matrix, you've got one 2 by 3 matrix, right? And what happens is when you use ref right? So what I'm going to do now is I'm going to create, let's turn the calculator on. I'm going to go back to names, and I'm going to use matrix C. Actually, I need to edit matrix C. Let's try that again. I'm going to go across and edit matrix C, right? And I need it to be 2 by 3. So 2, enter, 3, enter. And let me go back to Big Me. Right, and again, it's a bit hard to see, but I hope you can see that there are actually 3 columns there in the matrix, and I'm going to enter 20, 30, 100, 30, 50, 200 into that. In fact, let me turn the logo off. That way you can see it. Right, so 20, 30, 100, so 20, 30, 100, enter, and then 30, enter, 50, enter, 200, enter. Okay, and that's my matrix C. I can second quit, and then what I can do is I can do second matrix, scroll across to math, and then maybe I can hit alpha B. Then that'll select RF. That's the quickest way. You could scroll down all the way to RF in that list, right? You could scroll down to RF in that list if you want to, but you can use the green alpha button and select alpha B, and that'll select it directly, which is a bit quicker. And then second matrix and select C, and then close brackets. So now what I've got, let's try that again. What I've got now, so this is I put this in the C matrix, and now what I have is RF C, right? In fact, there's square brackets around the C to show that it's a matrix. And now I can just hit enter, and lo and behold, and again, you won't be able to see that quite as nicely as maybe you should. It's on this side, right? But what it says now is it still returns a 2 by 3 matrix, but it's a 2 by 3 matrix in reduced form, right? And reduced form means that in the, and let me go back to Mini-Me. Right, and what it means is in this part of the matrix, there's the identity matrix, which is capital I, right? And the answer we want is in the augmented part. And lo and behold, x equals -10 and y equals 10. Exactly like we got the other 3 ways we did the question. Everybody okay with that? And the fourth option is to use Matlab, and I think I have Matlab installed here, and I'm hoping it's going to start up somewhere. There it is. It's getting there. I'm always horrified at how even though our computers keep getting faster and faster, the software keeps getting slower and slower. It's a little silly, in my opinion. Okay, so there's Matlab, and I thought I should be able to make that a bit bigger so we can actually see it, maybe. fonts is what I want. Oh, it's thinking about it. There we go, fonts, and let's make that, I don't know, 36. Might be too big. Let's see what it does. That's probably right. And let's make that 36 as well. No, not 613, that's a bit big. See what that does. There we go. Right, so now maybe you can read it. So now I can do the same sort of thing that we did with a calculator in Matlab. I can say A equals, and I've forgotten the numbers, 20, 30, 30, 50. Right, A equals 20, 30, 30, 50. B equals, what was it, 100, 200? 100, 200. 100 semicolon 200. Right, and one way to find the answer is, I don't know whether this is going to work, but anyway, we'll try it out. The inverse of A times B. That worked. Another way to do it is Matlab has this backslash divide, matrix divide operator. So I can do that one, and that you can see is a lot faster. I can also do, there's a thing called inverse, and that does the same thing. And there's also another one which is better numerically called pseudo inverse. Uses singular values instead of eigenvalues. Right, and there's our pseudo inverse. And I can use RF if I really want to. In that Matlab stands for Matrix Laboratory, so it does all this matrix stuff just like your calculator does. And I can use RF where I've got the A matrix at one side, and then I'm augmenting it with the other information we have in the B matrix. Okay, I'm not going to do this example, except I'm going to do it using the calculator, and I'm going to use the RF version of the calculator, right? So the RF version goes 20, 30, 100, and then I'm augmenting it. Remember, there's that augmentation with 100, and then 30, 50, 100, 200, and then 100, 100, 200, 400. And now the augmented matrix is a 3 by 4 matrix. That's the one I need to put into RF. So I turn my calculator on, I go second matrix, and I'm going to put this in my D, so that's 4 on this one. No, I need to edit it. So second matrix, scroll across to edit, and then 4, and I said 3 by 4, 3, enter, 4, enter, and then I need 20, enter, 30, enter, 100, enter, 100, enter, 30, enter, 50, enter, 100, enter, 200, enter, 100, enter, 100, enter, 200, enter, 400, and that looks like it's pretty good. I always like to check that I've actually entered everything in correctly, because sometimes I miss a 0 or I get a sign wrong. So just read back through it again, and so that looks good. Then I'm going to go second quit, and then we're going to go second matrix, scroll across to math alpha B to get RF, and then second matrix, and I wanted my D, which is 4, and then close parentheses and hit enter. And I'm not going to show it to you because I thought the camera might be a bit better, but it's not great. So and then what I'm seeing here is I put, as I said, I put that into the D matrix. So I just did RF D. Right, whenever you put a matrix, it doesn't just put the D, it puts the square brackets around the D. And the result I get is 1 0 0 0 0 1 0 5 0 0 1 minus 0.5, right? And again, you've got this structure in the output of RF where here's your identity matrix, a matrix with zeros everywhere except on the diagonal, and on the diagonal you've got, the major diagonal, you've got ones. Okay, I think that was about all I wanted to show for the tutorial. Let's just go back and see where we are. Okay, so I talked about the lab, and I've talked about tutorial 1 questions 15 and 16. As usual, I'm going to take a 10-minute break now, and we'll come back, we'll talk about complex numbers. But before I do, does anybody have any questions about what I just went through?
Are you?
Yeah, go ahead.
Go ahead.
I was just gonna say, for the, I know you went over the lab questions, but that stuff you made on Excel, will you be putting that up on OneNote?
I'm not going to put the, I'm not going to do the lab for you, but the, if you go into Blackboard, the template I used is on the lab in Blackboard. Right. That,
What about that picture you took with the to measure the power? Are you gonna put that one up?
No, I'd rather you did that. Okay. You should just be able to take a screenshot and insert it into Blackboard, into the Excel spreadsheet.
Oh, understandable. I was just wondering about the formula for the power to calculate power.
Oh, that's already in the caps. Oh, sorry, I put it in the wrong. I've been putting it in the wrong. Sorry, I put them all in the wrong chat. Let me let me put them in the right chat. Sorry.
Thank you.
No worries.
It's okay.
Yeah. Sorry, I've got my capstone materials and I've been putting it in the wrong one. So let me. Yeah. Sorry, you should have said that earlier. Okay, let me just delete all of those out of the wrong one, and I'll put them in the right one. Thank you for bringing that up. And so the formula I'm using to calculate the power is that one. And then let's just go and grab those pictures. Where was that? One was in downloads. It's that one. So that was, I thought you could see that. That's the calculator picture. And then I'll upload the screenshot of the where's it gone? There it is. So screenshot of. You're welcome. That's the screenshot of what it looks like. What it that voltage times current looks like in LT Spice, and that's the screenshot of the Excel spreadsheet. And what was the other one? Yeah, I'll put that in there too. You need to do 2 others, so that's all right. That's that one. Let me just check to see if there was anything else I put across. Yes, the link to today's video. I should have. Sorry, I should have seen I was putting everything in the wrong one. That's bad of me. Okay, so there we go. That's that one, and I can delete that one as well. And okay, sorry about all that. I'm obviously suffering from lack of sleep or something. So any other questions about what we've covered so far, the lab or using your calculators to solve linear algebra equations?
For the lab, how can we label the power dissipation for the elements? Because I think you asked for that in the objectives.
The power dissipation. Oh, okay, so let's go. Did I just, I closed it. Let's open that up again. Okay, so all you need to do is once you've got the voltage and the current labeled, right? Then what you can do, let me just escape out of that and grab that one and scroll down a bit. What you can do is you can just, write it on here. P equals I1 VR1. I1 V1. Right, to get the power. And because you've got, it would be good because you know that the resistor is a passive device, and you've actually no, you don't want V1, you want VR1, because you've got the resistor labeled appropriately, right? You've got it's satisfying the passive sign convention. You can say that that's power dissipated by indicating that the power is coming out. If you really wanted to, you could also say that the power here, the power generated, is equal to V1 I1, right? Because this device is a power supply, so it's an active device. That's why it doesn't satisfy the passive sign convention. It's got the current flowing out of the positive terminal, but it's okay because it is an active device, so it's supplying power to the system. And funnily enough, it's supplying exactly the same amount of power as the resistor is dissipating. Okay, that answer the question?
Yeah, thank you.
You're welcome.
Professor, I know we're going to go on break for 10 minutes, but I just had one more question about the power. On LT Spice. Where exactly did you go to pull up that screen to add in power?
Okay, so if you've got this screen up, right, the one with the traces, you can right click on it, right click up here, right click in the title, and say
Okay.
add traces, right? And then I can do whatever, right? If I really wanted to, I could say time times v of n001, because that's another option, times I of r1 times I of v1, right? And that's a complete nonsense. But if I really wanted to, they're all valid measurements. So I could add those, and there's my the red thing is my my completely made up measurement. Okay.
Thank you.
You're welcome. And once we get towards looking at sinusoidal voltages and currents, etc., and even transients, that way of doing things is going to be much more useful, because we won't just get flat lines all the time. Okay, so let's leave it there for 10 minutes, and I'll be back and we'll talk about complex numbers. That's all right? So I'm going to go on mute, and I'll mute my mini-me as well. If I could actually grab it. There it is. Okay. Okay. So let's get back to it. The next thing I wanted to talk about today is complex numbers. And just to get a feel for it, has actually, let me see if I can put that. I've forgotten how to do that. Let me see if I can figure out how to do that. Yeah, let's go with that one. Pole faces. So this is going to be in the discussion. Interesting. For some reason it didn't like that. Oh, I've got to probably add it. How about that? Well, that one worked. So I've just put a poll into the discussion, and can you click on A, B, or C whether the answer to the question "Have you used complex numbers?" is yes, no, or what? Okay, we've got a couple of no or whats, and we've got okay, a lot of people have used. That's okay. So I thought it's worthwhile going through the background anyway, just because, if only because I use the letter J instead of the letter I. So let's just have a quick look through these slides. We'll make that a bit bigger. We'll close all of that up. Okay, so the particular piece, and I don't know whether I've got all of these in. let's go with red. It might show up a bit better than blue on blue, right? So complex numbers, background information. So when we normally talk about numbers, we think about the real line, right? Where we have some sort of an origin where the 0 is, and if we go in the positive direction, which is usually to the right, then we go in an increasing direction, or if we go in the decreasing direction, right, we get negative numbers. And it's really quite odd that people, when they first started thinking about numbers, well, for a start, they often ascribed mystical properties to 0, because 0 was the void, it was nothing, and that was a bit concerning for them. And then the other thing is that it took quite a while for people to think about negative numbers, right? And now we've got something even more complicated, complex even, where we could actually think about what happens not just in the x-axis, right, but what happens if we take a look at the whole plane, not just the number line. Now we've got a number plane, if you like. And that's where imaginary numbers come in. And the way we write an imaginary number, right, if I wanted to have this number here, that's 1 in the real axis, that's RE stands for real, and it's actually 1J in the imaginary direction. So one way to write this is 1 plus J, or 1 plus 1J if you want. There's other ways to write it. You can just do it like a Cartesian plot, right? An XY plot, so you could also write it like that if you wanted. Now, what we're going to look at is what happens when we rotate that unit vector, right? A unit vector is a vector that's 1 long. So what happens if we rotate that unit vector around the origin, and we look at the component of that unit vector that's projected back onto the real axis, right? So in the start position, right, the unit vector is completely on the real axis. It's completely in line with the real axis. So our value is up at 1. And then if we move to 45 degrees, then the projection of our unit vector onto the real axis is no longer 1, but it ends up being 1 on root 2, right, when we're at 45 degrees. When the unit vector is straight up, it's at an angle of 90 degrees, so it's completely imaginary, then the projection of that vector onto the real axis is nothing. It's 0, right? So now we've hit the 0 position. And we can continue doing that for various values, right? If we're going all the way back, then we project onto the real axis, we're now at -1, and then we eventually get back to 0 when we're down in the negative j-axis, the negative imaginary axis. And finally, when we get to our full rotation, 360 degrees, we get back up to 1, the unit vector being exactly in line with the x-axis, with the real axis. Okay. So really all complex numbers are is a shorthand way of writing down two vectors, right? Instead of writing out that, right, a 2 vector, we could just write x plus jy. And remember our j is what some people call I, and that this is the square root of -1. There are also other unit vectors, right? You could think about 3 vectors, because oftentimes if you're into mechanical engineering, that you want to deal with 3-dimensional space. So there's 3 unit vectors, I, j, and k. So my rationale for electrical engineers using j is that normally I in 3-dimensional space is used for the x-axis, and then j is used for the y-axis. We're only interested in a 2 vector, a 2-dimensional space, so that's where I think the use of j came from by electrical engineers, right? To that unit vector on the y-axis. Okay. Right, and there's lots of ways to write complex numbers. One way to write complex numbers was what we had up before, right? X plus jy. Another way is just the Cartesian coordinates. Another way is to draw them, right? And here we've got 3 complex numbers, although 2 of them don't have any imaginary component. There's a 2. There's a, what's that, a -3. And this one is what? It's about minus 2.2, 2.3. It's about minus 2.3 plus j. What's that, about 3.3, 3.2, 3.25, something like that. So yet another way to write complex numbers is you could think about using this length, right? This length here and this angle. So another way is to use polar coordinates. So these are Cartesian coordinates or rectangular coordinates, but these are polar coordinates. And all of these ways of writing complex numbers are equally valid. Some of them are more useful in some contexts than others. let me, so we've got Cartesian. I'm just going to take the two options. Which, if you were adding complex numbers, right? So if you're going to add two complex numbers together, I've just put another poll in the discussion forum. Which form do you think it's easier to use? The rectangular Cartesian form or the polar form if you're going to add? Okay, looks like everybody's saying adding. Let me see. Dylan, any thoughts on why you think it's easier to add using rectangular coordinates?
Because then I think you can just treat it like any other graph, like a grid, and when you add them together, it would just move it along to where it would be if you were just graphing something. You know what I mean? And with angles, it might be kind of different. I'm not sure.
Okay. Yeah. So if we've just got, if we add, if we add 2 and -3, right? We go 2 in that direction and then -3 in that direction to end up with -1, right? And the nice thing about the Cartesian coordinates is we can do the two axes independently. They don't interact when we do addition, right? So, for example, I can start with the orange vector and then I can add the number, this is really the number 2 plus j0 to it, right? And if I start off with the orange complex number and then add 2 plus j0 to it, I end up with something like the green one, right? So, and I apologize, I can't draw straight, but that should be a straight connection from the origin to the end of the red arrow. Okay. So let's ask the next question. So now we're dividing complex numbers. Now which way round is it? Is it easier to use rectangular coordinates or is it easier to use polar coordinates? And less committed here, we've got 5 people, 6. So Drew, on the you've said polar. Could you explain your reasoning why you think polar is better for division?
Honestly, I'm not too sure. I believe if you're using complex numbers with polar, it's kind of easier to have the radian values to work with.
Okay. Anybody else got any thoughts? Joel doesn't says he doesn't know. Any other thoughts? Okay. So I've held out on you a bit, and it's probably in the subsequent slides.
I think it helps cancel out the angles.
It does, but it's not clear from the way I've presented it so far, right? And there's a third way of writing complex numbers, right, which is called the exponential form, right? And it's very similar to the polar form, right? Right, so now let's think about two complex numbers, right? And we're dividing one number into the other one. R1 e to the j theta 1 divided by R2 e to the j theta 2, right? And that's just going to be R1 on R2, which is pretty easy, times e to the j theta 1 minus theta 2, right? Because 1 on e to the j theta 2 is just e to the minus j theta 2.
Okay, sorry, I think another reason why we have to use the polar for dividing, because the angles, we can add those angles.
Well, you could, yeah, you subtract the angles of the numbers, exactly. Okay, so in fact I'm hiding it behind my head there. That's what I was supposed to be showing you. Right, oh, I haven't been sharing my screen. I'm sorry. This is or have I? Oh, I have been. Sorry, I thought I'd stopped sharing for some reason. Okay. Yeah. So let's keep going. And like I said, there's Cartesian or rectangular coordinates. There's polar coordinates. And there's exponential form. And the exponential form is based on this equation, right? E to the j theta equals cosine theta plus j sine theta. And that is sometimes called Euler's formula from the Swiss mathematician who came up with it. Right? And so that gives us a nice connection between rectangular coordinates, which is what this is, right? This is x plus jy, and polar coordinates, at least for this unit vector, right? The magnitude of e to the j theta is 1, so it's a unit vector. More generally, this is the way to use it, where a is the length of the complex number, theta is the angle of the complex number, and then you can decompose it into the real part and the imaginary part, where by going a cosine theta is the real part and a sine theta is the imaginary component. I'm not going to go through it today, but I suggest you have a look at those two links. There is a slight problem with TI-83s and TI-84s. If you have a TI, I think it's 89, 99, the higher valued ones are okay. But later on, when we get to capacitors and inductors, what we're going to have to do is we're going to have to do exactly like we did in the linear algebra stuff just this morning, but instead of having real valued entries in the matrix, we have to have complex valued entries in the matrix. And unfortunately, the TI-83 and TI-84 won't let you do that. Not directly. So there's a trick you can use that video shows you that lets you use a TI-83 or TI-84 to do inverses of complex matrices, but it does it at the expense of complexity. What happens is if I have a matrix, let's say 1 plus J2, 3 plus J4, 5 minus J6, 7 plus J8. If I have that matrix, I can't enter that matrix into a TI-83 or a TI-84. What it gets you to do, though, is for every complex number, and let's just take the first one, it suggests turning it into a 2 by 2 matrix where the real part is first, then the imaginary part, then the negative of the imaginary part, and then the real part again. So you can enter this matrix, but it looks more like 1 minus 2, 2, 1, in this case 5 minus 6, 6, 5, 3, 4, minus 4, 3, and 7, 8, minus 8, 7. And you have to make sure that these two, the off-diagonal entries, are the negatives of each other, right? And you have to make sure that the major diagonal of each 2 by 2 are the same number. If you don't do that, it all falls apart. But if you do that, it means you can use your calculators to do the arithmetic. But have a look at those videos. It goes into it, and it shows the calculator screen much better than my earlier attempt today. There was one other thing that I probably should mention. I suggest use radian mode on your calculators, right? And the reason I suggest using radian mode on your calculators is if you use degree mode, you will almost certainly get confused when you think about e to the j theta. If you just enter this sort of formula into your calculator, theta has to be in radians. Whereas if you're used to your calculator being in degree mode, you will assume that theta can be in degrees. But I would suggest doing the whole calculation in using radians and only converting to degrees when necessary at the end, using the 180 on pi conversion factor. Okay, any questions about complex numbers? We're not going to use them for a while. As I said, where's the overview slides? Right, where is it? We're probably not going to use them until week 12-ish. So it'll be a while yet. And we will have a chance to go over it again before we start using it for circuit analysis. First of all, I need to take you through mesh analysis, nodal analysis, superposition, and Thevenin and Norton's theorems. Okay, if there are no questions, I'm going to check that one off. And I'm going to talk about mesh analysis. And again, I've got the summer 2019. That's when I put first. Actually, wasn't actually when I first put these slides, but it's when I put the initial run of this course by topic rather than by lecture together. So that's why it's dated like that. And that's the piece we need to talk about: mesh analysis. Did anybody remember what a node is?
Isn't it where all the currents equal 0 at a point?
Not quite. Anybody else want to chime in before I bingo somebody? Kyle Breton, do you have any thoughts on what a node is?
Yeah, it's like one piece of an electrical circuit where there's where the voltage is all the same. There's no resistance between any parts of it.
Exactly.
So it's between components.
Exactly. So it's I think I use the definition. It's an area of constant voltage, right? Which is exactly what you said. Right. That's what a node is. And the other thing we had was a loop. Does anybody remember what a loop is? Oops. Let's try that again. I can answer my question. I'm not going to answer my question. Somebody else can answer my question. I already picked on Dylan earlier today, so let me try someone else. Hunter, how about you? Any thoughts on what a loop is?
Isn't it a sorry, trying to remember from last other weekend. It's just the full, like, I don't want to say like the full circuit, but it's, cause I'm trying to remember the from Ohm's law where it equals 0, or where the voltage equals 0.
Right. So there's Kershaw's voltage law.
Or yeah, and then the current law.
Mm-hmm.
Isn't it? It's where you don't cross over, right, in a circuit.
Right. Exactly. So it's a closed path through the circuit,
Yeah.
And it's got to be that it doesn't cross itself. Okay, so they're two of the definitions of pieces of a circuit. And nodes are important because they tell us whether things are in series or parallel, depending on how the connectivity is arranged. And nodes are also important for Kirchhoff's current law, right? Remember, Kirchhoff's current law is all of the currents flowing into a node sum to zero, right? And a loop is important for Kirchhoff's voltage law, right? And Kirchhoff's voltage law says that all of the voltages around a loop equals zero. So a mesh is a very special sort of loop. Okay, so here's I think a circuit that we've looked at before. And I'll just, first of all, I'm just going to use it to, let's see if I can copy that, and I'm just going to go over here and see if I can paste it into here. Yeah, I can paste it into here just as a copy, right? So I'm going to graffiti it, and I want to actually use it for the mesh analysis example. So let's have a look at the nodes, right? I'm going to draw the nodes in green. There's a node here, right? Remember, a node is an area of constant voltage. There's a node here. There's a node here. And then there's the reference node, because we've got our ground, our earth, our zero voltage reference. And so this is a pretty big one. And I can't draw long straight lines, so apologies for that. Right, so there's 4 nodes in this. And let's go with loops. Right, there's a few loops we could define here. We could define a loop this way. We could define a loop this way. And we could also define a loop that way. Right, so there's 3 distinct loops in this circuit. A mesh is a special sort of loop that doesn't cut an element. A circuit element. Right, so in this circuit, we're just looking at the 3 loops. This loop, the small one, that doesn't cut a circuit element. This small one doesn't cut a circuit element, but this one cuts a branch, cuts the branch there and there. So the only meshes in this circuit are those first two loops. Okay, the big one, the one that goes all the way around the outside, that's a loop, but it's not a mesh. Okay, so let's go back to our... So this example is first of all aimed at just using what we already know to solve the equation. And what do we already know? We already know how to combine series and parallel resistors together. So we're asked to find VA in this diagram. So the first thing we can do is we can combine R3 and R4 because they share a common node, so they're in series. And then that R3 plus R4 series resistor is in parallel with R2. So we can redraw the circuit like that. Right, so R3 plus R4, those were in series, and that equivalent resistance is in parallel with R2. So we can redraw the circuit like that. And this is saying, so now VA, we can use our voltage divider equations and say that VA is equal to 12 ohms divided by 12 plus 6 ohms times the input voltage. And remember, the small plate is the negative and the large plate is the positive. So really the voltage applied here is minus 21 volts. Right, and that's going to be 12 on 18, which is 2/3. So VA in this instance is minus 14 volts. Now, there's a more algorithmic way to do this, and the way to do it is called mesh analysis. And this is the first algorithm, as I said, of probably 5 algorithms we're going to look at. Some of them are more complicated than others. The two big ones are mesh analysis and nodal analysis. So the algorithm goes, assign mesh currents, and let's forget about super meshes for now. I'll explain what a super mesh is a little bit further down the track. Use KVL on each mesh current. Use Ohm's law to express the resistor voltages in terms of the mesh currents. Distribute and group like terms. Plug in values and solve the system. Okay, so let's see how that goes on our circuit, right? Here's the same circuit we started with, and I've identified the meshes. And these are mesh currents. So there's I1, the red one, and I2, the blue one. So we've done the first part. We've identified the mesh currents. Use KVL on each mesh current. So in order to use KVL, we have to identify all the voltages, right? KVL is Kershaw's voltage law. And Kershaw's voltage law says the sum of the voltages around a loop, and a mesh is just a special version of a loop, sum of the voltages around a mesh are 0. So let's figure out what the voltages are, and remember we want to, if the device is a passive device, it has to satisfy the passive sign convention. If it's an active device, it keeps its own polarity. So this voltage source is an active device. It's not passive, so it keeps its own polarity. And then, because our current is flowing around this way, our red current, our polarities are like that for the voltage across R1, and our polarity is like that for the voltage across R2. So what are we doing? We're applying Kershaw's voltage law. So for I1, KVL says, what does it say? It says we going into the positive of Vs, it says that Vs, and then we're going into the positive of R1, so plus VR1, and we're going into the positive of R2, so plus VR2 equals 0. So that's the Kershaw's voltage law for the I1 mesh current. Okay, so we haven't finished yet. We've still got to do Kershaw's voltage law for the I2 current. So let's go with blue, right? And again, we've got our loop current direction defined. And now all we have are passive devices. They're just resistors. And we have to have each of those passive devices satisfy the passive sign convention. So now my signs look like that. And notice that VR2 from the perspective of this current is different polarity from the I1 perspective. That is okay, right? The current directions determine for passive devices what sign is there, and you have to have, going into a passive device, you have to go into the positive terminal. So now we can write down the blue components. So for I2, KVL says, well, what does it say? It says VR2 plus VR3 plus VR4 equals 0. Okay so far? Okay. So we've applied KVL on each mesh current. Now we've got to use Ohm's law to express the resistor voltages in terms of the mesh currents. So let's do that. Let's have a look at what Ohm's law tells us. Well, so for the red one, we already know that Vs is 21, so we can just write that down. VR1, the only current flowing through R1 is I1. So VR1 is just I1 R1. R2's a little trickier. R2 has I1 flowing that way through it and I2 flowing in the opposite direction through it. So VR2 from the I1 perspective is I1 minus I2 times R2, because the total current flowing through R2 is I1 minus I2. And again, that whole thing equals 0. Okay, let's do the same thing on the I2 mesh. Now VR2, again VR2 from the I2 perspective has I2 minus I1, so I2 minus I1 times R2, and then VR3 is just I2 times R3, and VR4 is just I2 times R4, and again the whole thing equals 0. Now I'm just going to, I've done it algebraically, but we do have some numbers for each of these devices, right? So I'm just now going to go back and say, so for this one, that's going to be 21 plus, now R1 is 6, so it's 6I1, and R2 is 24, so that's plus 24 times I1 minus I2. And then on this side, it's going to be I2 minus I1, and it's times 24. And then R3 is 14, so 14 I2, and R4 is 10, so plus 10 I2, and that equals 0. Okay, so I've applied Ohm's law to each of the meshes and each of the resistor voltages within each of the meshes. And now I've got to distribute and group like terms. So let's have a look at that. So on the red side, I've got 21 plus 6I1 plus 24I1, distributing the 24, minus 24I2. And let's just get that into a bit better form. That means we get 30I1 minus 24I2 equals, and we'll bring the constant over the other side. So that's one equation. And then this one, we've got 24I2 minus 24I1 plus 14I2 plus 10I2 equals 0. And now I've got 24 plus 14 plus 10, which is a total of 48. So I've got minus 24I1 plus 48I2 equals 0. Now I suggest you write all of your equations so that you've got your currents in the same order. Otherwise you will get confused, right? So now what we can do is we can rewrite that as a matrix equation, right? And I suggest you get into the habit of just going straight to RF, right? So it's 30 minus 24 minus 21 minus 24, 48, 0. And I'm going to cheat and go with Matlab. Right, so this is mesh 1, and I've forgotten the numbers already. 30 minus 24, 30 minus 24 minus 21, and then minus 24, 48, 0, minus 24, 48, 0. Right, and then I can just do RF mesh 1. Okay, and I get that I1 is minus 1.167. So that's telling me that I1 is minus 1.1667 amps, and I2 is, I think it's 0.5833. Yeah, minus 0.5833 amps. Now I still haven't figured out what VA is, right? The question's asking what is VA. And there's a couple of ways we could get to VA, but I'm going to go with the most direct one. And the most direct one is just the voltage across R2, right? On one side of... hello? Yeah?
Real quick, my bad. You think you could show the Matlab code?
Okay, so I just typed in the mesh 1 is the 2x3 matrix with all of the coefficients in our equation, and then I just typed in, I just used the RF function.
All right.
Okay.
Thank you.
You're welcome. And I can put that into. Hopefully, I get the right. Where's it gone? There it is. Right, I just put that into the materials channel as well. Okay, so how do I get the VR2? Well, really I want the red version, because otherwise I sort of go negative on the blue version. So my VR2 from here is just I1 minus I2 times R2, which is just 24 times I1, which is minus 1.1667, minus negative, so it's plus 0.5833, and let's see what that comes out to in Matlab. So it's going to be 24 times, and it's going to be I1, so that's ANS 1,3 minus ANS 2,3, I think, if I get my indices correct. And lo and behold, the answer we get out of that is minus 14 volts, which is the same as the answer we got doing it the possibly quicker way for this particular circuit, right? We just did the series and parallel resistor combinations to find equivalent resistances. The good thing about this way of doing it rather than the other way, though, is this applies in much more complicated circuits.
Why do you have to use R2 and not like R1 or R3?
To get, so the voltage we're after is the voltage here, right? And it's usually the voltage is referenced to our V equals 0. So that's what I was saying, that you could, there's other ways to get the answer. The way I took, and let me just get a different color maybe. Let's go with that one, the orangey one. right? The way I took is just taking this voltage here, right? The voltage across R2. But we could also go from here, which is the same node, right? It's the same reference node. We could go here and go like that, right? And let's see what that one gives us, right? So this one would say that VA equals, where we're dropping 21 volts, right? We're going from the positive side down to the negative side of VS. So it's going to be minus VS. And then we only have I1 going through that. And I think we're going to have to add that. So it's going to be I2, sorry, I1, it's I1 times R1, right? And so it's going to be minus 21 plus I2 times I1 times R, so 6 times 1.66. So 6 times 1.1667, that's about 7, right? So that's plus 7, and that also gives us minus 14 volts. And then the other way we could go there, let's go with the mauve color, is round this way, right? And that round that way, the only thing in the way is we've got well, we're going against I2, so it's going to be basically 24 times I2. There's no other voltages, and I think you'll see that that's going to be also going to be minus 14. Close enough. I didn't get enough significant figures, right? So that's going to be also going to be minus 14 volts, right? So we get the same answer regardless of which direction we approach the node from. I just took the most direct approach, just going through the one device. Okay, I'm just going to have a quick look, right? And there's more complicated circuits we could look at, but I think that is probably a good time to take a break. So let's do that. Does anybody have any questions so far about mesh analysis?
For I1, like the third to the last red line where it says 30 I1, where's the 30? Oh, never mind. I'm stupid. I see it.
You're right. You got it. It's
Yeah.
yeah. I'm just adding these two together.
Yeah.
Right.
My bad.
That's okay. Okay. So let's leave it there. Again, let's take a 10-minute break. I'm going to go grab a snack, and I'll see you back. I'll go through some more examples in here, but what I might do is I might have a quick look at the tutorial sheet as well. Okay, so let's just start up that 10-minute timer again. Any other questions before we go to break? Okay, let's oh, sorry, what's that? What was that? Are we expecting what? Sorry, I'm missing the last word.
Are we expecting the lab?
What about the lab? Sorry.
I'm asking, are we expecting a lab today?
So yeah, I will. I think I said earlier at the beginning that there will be another lab and another homework released later today, but it won't be due for 2 weeks.
Right, thank you.
Okay. Okay, so let's start that up, and I'll go to a bit of a break. Thank you, everyone. Okay. So I forgot to check off the other two things we did, but let's just go over the algorithm again. Part of the reason in the lab that's due today that I want you to label your currents and your voltage polarities is because it gets super important when we start doing mesh analysis or nodal analysis. And that's why it's the first thing in the algorithm, the first step in the algorithm. Assign the mesh currents. Then we apply KVL. Now, remember what I did to, it started leaving stuff around. I'm just going to quickly quit out of OneNote and start it back up again. Because when it starts leaving garbage around the screen, it keeps leaving garbage around the screen. Okay, let's see what happens. So I did explicitly write down KVL, right? I wrote down the, right, this was my, I don't know whether I can, so this was my writing down of KVL for the first one, and this was my writing down of KVL for the second one, right? I didn't write down currents directly. I didn't use Ohm's law directly. I suggest, at least when you start applying mesh analysis, that you do the same, that you do it step by step. You can, once you get okay at it, and I'm going to go back to a standard pen, maybe. Once you get okay at it, you can go straight to that line, or straight to that line, right? Because it's pretty clear. But I suggest, at least in the first instance, that you write down the actual names of the voltages, VS, VR1, VR2, VR3, VR4, in the appropriate Kershaw's voltage law equation first. Okay, so here's a slightly more complicated one, right? And you'll notice I've already, for the first example, I'd already done step one for you, right? I'd already assigned the mesh currents, and here in some ways I've done even more. I've not only assigned the mesh currents, but I've indicated the polarities, at least on the passive devices. You'll notice though that now I've changed the direction of I2, right? In the previous example, I2 was going, what's that? That's clockwise, right? Let's go with, I don't know, let's go with the mauve color. So here I2 is going clockwise, and it's the same direction as I1, clockwise. They don't have to be the same. I would get exactly the same answer if I had both I1 and I2 going counterclockwise, or if I had I1 going counterclockwise and I2 going clockwise. or vice versa, right? So this example, notice that I2 is now going counterclockwise. I would suggest, just to drive the point home, that you also label the polarities of any active devices, even though, yes, the large plate is the positive plate. But just to remind yourself which is which, please label the polarities of any active devices as well as the passive devices. Let's just check that the polarities are there correctly, right? So we've got our I1 going this way. This is a passive device and I1's going into the positive side. This is a passive device and I1 is going into the positive side. This is a passive device, R3, and I2 is going into the positive side. And then I2 is going into the positive indicated side of R2. So we're all good as far as the passive sign convention is concerned. Right, so we've done step 1, assign the meshes. Next step is to write KVL for each mesh. Okay, so let's see if we can do that. So KVL for I1, well, I1's going into the negative side of this, so it's going to be minus VS1. It's going into the positive side of here, so it's plus VR1. And then it's going into the positive side of that, so it's plus VR2 equals 0. Let's do the same for the other side. So KV, let me just move it down a little bit so I've got room to write steps 1 to 5. So KVL for I2, and now we've got a minus VS2, right, plus VR3 plus VR2 equals 0. That all looks good, and I forgot to write the equals 0 here. So now the third step is to write voltages in terms of mesh currents using Ohm's law. Okay, so let's do that. Well, our VS1, let's just write down the number, so it's minus 12, and then plus VR1 is just 6I1, and then now the voltage across R2, VR2, is 12 times. The total current through R2 is I1 plus I2 now, because they're both going in the same direction. That equals 0. And then VS2 is 8 volts, so minus 8 volts. VR3 is plus 12 times I2. And VR2 is again, this case looks exactly the same as the other side. 12 times I1 plus I2, and that equals 0. Okay, next step is, let's go with red. Next step is distribute and group like terms. Right, so that's minus 12 plus 6i1 plus 12i1 plus 12i2 equals 0. So that's 18i1 plus 12i2 equals 12. And then on this side it's minus 8 plus 12i2 plus 12i1 plus 12i2 equals 0. And so that's 12i1. Remember to put it in the same order, i1, i2, plus 24i1 equals 8 when we take it over the other side. So our full... Yes, a question?
Can you simplify these? Like, can you take out a 6 from I1?
Sure.
Or red one?
Sure. Like, yeah, right. So that's sometimes that's worthwhile doing, right? Just makes it simpler to write. So you could take out you could divide both sides of this equation by 6, and you could get 3i1 plus 2i2 equals 2, right? It's the same equation, it's just scaled down a little bit.
Alright, just making sure.
Yep, and the other one you could think is a common factor of 4, right? So you could go with 3i1 plus 6i1. Sorry, that should have been i2. I miswrote that. So 6i2 and divide by 4 is 2. Okay, good question. So then we can just write out our RF, and I suggest you, if you are going to use RF, that I suggest you write it out in your working. Makes it easier for me to check your result in case something's amiss. Okay, 322362. And let's just pull that up. So this is mesh 2, and there's 322362. Okay, so our I1 is 2/3 of an amp, and our I2 is 0. Let's just excuse me, let's just quickly look at the other version, right? RF 18 12 12, and then 12 24 8. Okay, I'll just move that up a bit so I can still read it. There we go. So mesh 2A equals 18 12 12 12 24 8. Oops, didn't mean to do that, I meant to do that. And then RF mesh 2A, and we get exactly the same answer as the simplified version. Okay, I thought it might be good to have a look, if I can figure out where it is. There it is. Um, So this isn't your midterm, this your second midterm. This is the second midterm I did in summer last year. Right, you can see it's dated July 2020. And this is the sort of question I would ask you during an oral exam. And in fact, it's a bit perhaps a bit easier than what is seen here, in that I will give you this exam paper, and remember this is the second one. The first one is about the basic stuff that we've already covered, and I will ask you to talk me through solving one of these mesh analysis problems. Right? You only have to do one, but I get to choose which one. And then the other question is to do something similar, but with nodal analysis. And we're not going to cover nodal analysis for a while yet. Okay, and you can see the complexity of the circuit is a little bit more complicated than what we've done so far, but that's okay. This is going to be the second midterm, which is probably quite a way away. And just for reference sake, let's have a look at the summer's first midterm, because it's going to look pretty similar to right? And again, there's several different questions. Sorry, there's 3 different types of questions. One about charge, one about resistivity, one about resistance change versus temperature. And I will give you something like this paper before the midterm. And then the way I work is I choose one of the charge questions, one of the resistivity questions, and one of the resistance versus temperature questions, and I'll get you to talk me through how you would answer it on the call, on a Discord call. And once you've done that, I'll give you some numbers, and I'll get you to work through the numbers outside of the Discord call and upload your answers into Blackboard. Okay, and just for completeness sake, it's going to probably scare you, but that's okay. I'll just quickly pull up if I can figure out which is the 2020 file. I think that's it there. Where's the PDF gone? There it is. Right, and again, this is the online final, and now we've got inductors and capacitors in the circuits, and we've got sinusoidal voltages, and we've got funny triangular looking things which are called op amps. And we've got slightly different circuits, and we've got transient circuits. Okay, and that's the format of the final, just for completeness sake. Okay, any questions about the stuff I've done with mesh analysis so far?
Yeah, I have a question. I'm just kind of trying to wrap my head around why VS1 and VS2 are negative, and if they're negative, I know how R1 and R2 is positive. So meaning, if VS1 was positive, would R1 and R2 be negative?
Okay, so the issue is you want to know why I've put, let's just get a different color, why I've put, oops, oh, I changed it. So the issue, sorry, it just froze for me.
I mean, I can understand why it's negative, but like, how do you know it's negative? Like, because I'm looking at this and it's kind of like, I know it's rotating this way, so it's going that way, in that, direction. But it's just like, let's say if I do this myself, it's like, how would I know it's negative or positive by myself?
Well, the reason you know is because you've defined the direction of the current, right? And in this case, for the voltage supply, you've shown it, for the direction of the current you've chosen, it's going into the negative side. And because it's going into the negative side of the active device, that means you have to negate the voltage in the KVL, right? Because you, and then the other side of that is for passive devices, you have to define the voltages according to the passive sign convention. So you're always going into the positive side of those devices. So whenever you add a voltage across a passive device, you're just adding it, you're not subtracting it. The only ones you should be wary of are the active devices, the voltage sources. There you have to make sure you know what the polarity of the voltage source is. You can't choose the polarity of the voltage source. The voltage source polarity is chosen for you, right? But for the passive devices, you're effectively choosing the polarities there by your choice of current direction. Okay, I don't know, does that help?
Yeah, it does. Thank you.
Okay. So, right. What was that?
Sorry, I got one more question. For R2, how do you determine the sign when multiplying it by I1 and I2? Like it says 12 I1 plus I2. How do you know when I1 and I2 is a certain sign?
Okay, so it depends. Let me just let's go. There we go. So right, there's a few things you've got to look at, right? So let's just draw that, and we've got that. Say we've got that resistor, and say it's R2, right? And we've got on one side, we've got a current I1, and on the other side, we've got a current I2, right? The total current going through R2, right, and I'll try and draw it, is I1 plus I2 in this instance, because they're both going in the same direction. so they reinforce each other. Whereas if I had the same resistor, R2, and I had the same I2 direction defined, but let's say I chose I1 direction defined, but I chose the I2 direction to be the other way. Now I1 is going in that direction and I2 is going in that direction. Now we've got a bit of a quandary, because it depends now. Remember, in the first case, in this case, because I1's going this direction, VR2 is there, is the polarity of VR2 is like that, and here the polarity of VR2 from I2's perspective is the same. They're different here. Here, that one from the perspective of I1 is like that, and I drew it, I should have said I2 there. From the perspective of I2, right, to make sure that R2 follows the passive sign convention from the perspective of I2, you've got to have that positive sign. So now we've got counter signs. So now what's happening inside R2? Well, from the perspective of I1, meaning we're looking at this voltage, we have R2 times I1, and I2's going in the opposite direction, so we subtract I2 from R1. That's from the perspective of I1. From the perspective of I2, right, now the voltage direction is that way, right, because we go from negative to positive, and now VR2 from the perspective of I2 is I2 minus I1.
All right, that helped a lot. Thank you.
You're welcome. Okay. The directions of currents, of mesh currents, are completely choosable by you, right? The only caveat, the only thing you've got to be wary of is that you need to make sure that passive devices follow the passive sign convention for the direction of current you've chosen. And when you get devices with multiple mesh currents flowing through them, usually you only get 2 mesh currents maximum, then you have to be wary whether you're looking at it from the perspective of I1 or the perspective of I2. And they'll give you the same answer, it's just one will be the negative of the other, right? You can see the orange one and the green one on the screen. One's just the negative of the other. And that just means that the green arrow is upside down from the orange arrow in the bottom diagram. What's happening? For some reason it's not wanting to scroll my fingers. Okay. Now it is. Wonder what that was about. Okay. I'm not going to go through this example today. I will go through it next time. What I thought we should do quickly now and I'll probably end the session a little early. What I thought we should do is have a quick look through two things: the tutorial sheet, and I'll get the next week we'll have a look at doing the tutorial sheet in class. Right, so here's the tutorial sheet. I don't think I've put this in Blackboard yet. I will make sure I do that. And make sure that I put the other one up in Blackboard too. Right, and so here's an example. Right, the first question. And it's a simple one, but we've got... I think you should be able to see that here we end up having 3 meshes, right? And this particular circuit, we could just do what we did before and have those 2 in parallel and that equivalent in series and that in parallel, and then that in series, and we could just block it up like that. But the aim is to allow you to do that if you want to check your answer, but then apply mesh analysis to the same circuit. And here's another one, and this one's a little different. For a start, the thing we're trying to find is no longer a particular voltage. Now we're trying to find a current, and again we've got 3 meshes in this circuit, and the current we're after, Ix, is going to have 2 of those currents flowing through them. Right, depending on which way we define the mesh currents for the middle and right hand meshes, we may do something different. The other thing that this one is doing is it's got, I think it's one of the first times we've come across a current source rather than a voltage source. And there's some special things about current sources, and that's what I want to talk about briefly after we've had a quick look at this. And now we're ramping up the complexity a little bit more, right? And the additional complexity in this one, even though there's only 2 meshes, there's a couple of things. The main complexity here is that now we have a dependent source. So we're not, even though I know a lot of you will make the mistake thinking that VS2 equals 8 volts, but that is wrong, right? This is saying 8Vx, and Vx is that voltage there, right? So be warned that when you see a diamond source, that means it's a dependent source, and if it's a voltage source, it's going to be the voltage it outputs is going to be dependent on some other variable in the circuit. But there's only 2 meshes in this, so it's a little simpler. And then here's another mesh analysis with a dependent source in it. And again, that's not 10Vx on Vs1. It's not 10 volts on Vs1. It's 10Vx, and Vx is defined as the voltage across R2. So have a look at those during your week, and we'll probably spend the first part of next class session going through them. I did just want to quickly mention some special properties about what you do with mesh currents when there are current sources, right? So let's just say we define I1 there, and we define I2 there. Can anybody tell me, and let's just kill all of those. Can anybody tell me what might be special in this case? And David Dubac, you've got any suggestions as to what might be special now that we've got a current source in the right-hand mesh? No? Okay. Let's call on someone else. Spencer?
The question was, what was the question about the current on the left?
Well, so the is there anything you can tell me about, well, either of the currents, but particularly about the current I2?
Beyond that, it's a constant current source and not a constant voltage.
Okay, yeah, it is a constant current source, so that's should be a clue to something that I'm looking for. Okay, let me try someone else. Ryan, do you have any? Oh, you made it. Good. You got any thoughts on what might be happening with I2? No answer? Okay. Let's try...
Professor, can you hear me now?
Yeah, I can hear you now.
Oh,
Yep.
okay, yeah, sorry, my mic was having issues. I said that it might be an issue with, or it might be something to do with the loop getting thrown off because you're having an actual change in current as you go through.
Okay, so that's an interesting way of putting it. So the fact is, I think Stephen just put something in the chat there. Change of current. The fact is there is no change of current, right? So because I've defined I2 to be the current in that mesh, and because I know the current through this circuit element is 5 amps, I can write down immediately that I2 equals 5 amps. Right? So one nice thing in this instance is that current sources simplify the analysis when there's only one mesh going through the source. So that's a nice thing. So when you're doing mesh analysis, and sorry, I've written it behind me. There we go. When you're doing mesh analysis, if only one mesh goes through a current source, you've already got the value for that current. You've already got the value for that mesh current, right? You're done for that particular current, which is nice. unfortunately, there's a problem, right? If you have, and I won't read out what here. If you have a circuit more like this one, where again we've got a current source of 5 amps, but now we've got I1 and I2 flowing through it, that's a problem. Any idea why that's a problem? Okay, let me see if I can ask somebody. Mehul Kumar, do you have an idea why having 2 mesh currents flow through a current source is a problem for mesh analysis?
I'm sorry, I don't have any idea.
That's okay. And John Wertz?
Hello, can you hear me?
Yeah, I can hear you now. Yep.
If I had to guess why having more than one current source flow through it would be it could overload whatever you're running it through, maybe.
It's actually it's I don't know, it's a bit more, I don't know, cerebral than that, right? So the issue is when you're doing mesh analysis, right? You apply KVL, and the trouble with current sources we probably want plus and minus that way. The trouble with, well, maybe the other way. The trouble is we have no idea what the voltage drop across that source is. We don't know, and we can't know until we've finished the analysis, right? So because we don't know what the voltage drop here is, we can't do KVL here, and we can't do KVL here, right? Because we can't add in the voltage. What some of you will do is you'll see this, and for let me just erase some of that malarkey, right? So what some of you will do is when you'll write down the KVL for I1, and you'll go minus 10 volts plus 1 times I1 minus I3, right? Because I3 is going in the opposite direction through this resistor. And then you'll come here and you'll say that that's plus 5. And then you'll say plus 1 times I1 minus I2. And then that's equal to 0. The error is that you will have added a current to voltages, right? You can't do that. And because you can't do that, you've effectively got to put another unknown in there, a V5A. So that's the reason why in now that we've got two mesh currents flowing through a current source, that there's a problem, because we can't now apply KVL because we don't know the voltage drop across the current source. So that's where the idea of a super mesh comes in. And a super mesh says, okay, normally I would get KVL for I1 and KVL for I2. But I can't do that now because I've got this shared current source. But I still need to generate two equations. I can generate two equations, and I can do the following. Right? I can look at this current source, and whereas if I just had I1 going through it, I could just write down I1 equals 5 amps. But I don't. I've got I1 minus I2 equals 5 amps. So I have effectively a KCL equation, which is I1 minus I2 equals 5 amps, right? And then the other thing I can do is I can do this, as it's labeled, I can do this super mesh. Right, so I can follow a line, and it's actually more like a loop, because it actually does cut one of the branches, but KVL still applies, and now I get the KVL for the super mesh. So I get minus 10 volts, 1 I1 minus I3, what's that going to be, 1 I2 minus I3 times 3 plus I2 times 2 equals 0. Okay, so I replace my two KVL equations with a KCL equation and a super mesh KVL equation. Okay, that's about where I want to leave today. What I'd suggest, finish today's lab, please get that in. What I'd suggest between now and next week is that you have a look at the tutorial questions, the first 4. We're not going to start nodal analysis for a little while yet, so I suggest you have a go at certainly question 1 before next week, and then the first up next Saturday we'll look at, I'll see if I can get somebody to talk me through a solution to question 1 and potentially the other questions too, if you've managed to get them done. Let me just check. I don't know whether this one has, I don't think this one has a good super mesh example question. So I'll try and put together a few super mesh questions for later as well. Okay, anybody got any questions about any of that? No? If not, thank you for your time.
Professor?
Yeah, what's up?
I have a quick question. It's related to the lab we did last time. I know you sent an email saying I don't know if it was the lab that was supposed to be done last weekend. But I just want to know if the way I did it was the right way, because I was not sure, because I filled the Excel file, put my name on it, and I did the screenshot, and then I wrote, is that how the lab is supposed to be done.
Yeah.
Okay.
Yeah. So I don't know. Let me just check to see. Oh, it's logged me out. Yeah. I mean, I haven't. I had graded everything that was available, but I haven't looked at it in a couple of days. So let me just. What I'll try and do is by Monday I'll try and have graded all of the outstanding assignments.
So the one that's due tonight, correct? The one that's due tonight is the lab 2, right? Lab 3, is it also due tonight? Because it says that it's due at 12:59, 11:59.
Lab 3? There isn't a lab 3 yet, is there?
I mean, a lab 4, I believe, if that's it. There's 2 assignments. There was only one when I, in the morning.
Right.
And then in the afternoon, you said you were going to release another one.
That's correct.
So that second one that you released, is that going to be due tonight, or is it due, next weekend?
It's due in 2 weeks' time. So today I'm going to release another lab and another homework assignment, and they'll be due in 2 weeks' time. Okay, that's why I suggest you spend some time this week looking at the tutorial questions, so that we can. I think that'll be better preparation than forcing a 1 week time homework on you. Okay.
All right. Oh yeah, there's a lab 2 which is due almost.
Yeah, lab 2 is effectively what I went through in the first part of today's session.
Yep, and all right, thank you.
Okay, you're welcome. Anything else? If not, let's leave the session there, and have a good rest of your weekend.
Thanks, Professor. Have a good night.
Yeah, you too. Bye bye.
Thank you.